So in this video, we're going to talk about standard deviation and the normal distribution. So in this problem set, there are some pretty good problems talking about regarding standard deviation that there's a quick way to do it and there's this very slow way to do it in which you actually compute the two differences and all that. So we'll get to that when we go into problems. But before that, let me briefly talk about standard deviation and normal distribution real quick. So, standard deviation is a measure of how much variation the data has with respect to the mean. So the bigger the standard deviation, the more variation there is from the mean or the average. The smaller the standard deviation, the more tight the distribution is, which means the values are close to each other and close to the mean, okay? So let me give you a few examples. Actually, let me first write out the general formula. So usually we say the variance, which is standard deviation squared, we say the standard deviation is sigma, so variance is sigma squared. We sum up I equals 1 to n, x sub I minus x bar squared over the number of terms. Okay, so you're gonna, for each term in the set, you're gonna subtract it from the mean, square it, and then add it to, do the same thing for each term and add them all together. And then you're gonna divide by the number of terms. So that would give you the variance, and standard deviation is just the square root of this. Okay, so variance is always a positive number because it's squared, and therefore standard deviation is always positive as well. So you can never have a negative standard deviation. Okay, and as I was saying, let's say your mean is somewhere here, okay? If you have a very fat distribution, so something like this, I don't know, something like this, your standard deviation is quite high because here's your mean. There's lots of values here and over here, okay? Versus, let's draw the mean over here again. If the distribution looks something like this, distribution means like a histogram. If it's like this, let's make it very sharp to contrast. Most of your values are very close to the mean. So the standard deviation is small. Okay? Because remember, the formula is kind of the distance from the mean and is squared. So these are all pretty close to the distance, but here you have some that are far out over here. So that's why the standard deviation is higher or larger over here. All right, so that's on standard deviation. Now the normal distribution, sometimes it's also known as the bell curve, looks something like this. All right, why did they say it's normal distribution? Well, a lot of things in the real world, they have a distribution that looks like this. So that's why they say it's normal distribution. For example, random variation looks like this. You have something centered at a target, the mean. So let's say you're in a manufacturing line. You need something, you're making rulers, let's say. A ruler, let's say it's 1 foot, so 12 inches or 30 centimeters. So that's your target. You want to make each ruler exactly 12 inches or 30 centimeters. But in any real process, there's going to be some variation. Whether it's a machine that makes the ruler or a person that makes the ruler, is never going to be exactly 30 inches. It might be like, 30 centimeters. It might be 29.99 centimeters, or sometimes it's 30.0001. So there's going to be some variation, all right? And in the real world, when it's just random variation, then it's a normal distribution. That's a very common assumption in the real world. Okay, so why are normal distributions useful? This is a very coarse approximation. This is actually not quite right. But it's all dependent on the standard deviation sigma. Okay, so if you go 1 sigma in both directions from the mean, then that's about 68% of your distribution. Okay, if you go 2 sigma, so 1 sigma, 2 sigma, and then 1 sigma, 2 sigma the other way, it should be about 95% of your distribution. So this estimate here is not quite correct. It says normal distribution, but usually it's around 95%. Right now over here, it would say 96%. So a little bit off, give or take. And then if you go 3 sigma, doesn't show it here, that's 99.7%-ish. All right, so that's why normal distributions are helpful. It's all dependent on sigma only, sigma and the mean. If you know the mean, and the standard deviation, you know everything about the distribution, basically. Okay, so now let's dive into the problems. We spent about 5 minutes on talking about that. That's okay. So questions 1 to 3 refer to this curve, this bell curve. Figure shows a normal distribution with mean m and standard deviation d, including approximate percentages of the distribution corresponding to the region shown. So notice it's approximate percentages. Suppose the SAT math scores of 1,200 students entering a certain university are normally distributed with a mean score of 600 and a standard deviation of 60. Approximately how many of the students have SAT scores between 660 and 720? So go ahead and try to solve this one first on your own. Okay, so let's actually fill this out. So if the mean is 600, standard deviation is 60. So over here would be 660. Next would be 720. Okay, and similarly over here, maybe we don't need that. So let's leave it blank for now. Approximately how many students have SAT scores between 660 and 720? 660 and 720. Okay, that's about 14% of the students. So what is 14% of 1,200? So 1,200 times 0.14. So what is that? That is 12 times 14, which is 120 plus 48, which is 168 students. Okay. Next, how many students have SAT scores less than 540? So go ahead and try to solve this one. All right, so we need to fill in these values then probably. So 600 minus 60, 540, minus another 60. Let's just do it now. That should be 480. All right, so it says how many students have SAT scores less than 540? So it's 540 and below. So what is 14 plus 2? That is 16% of the students. So 16% of 1,200. So 0.160, right? All right, so this is 12 times 16, which is 120 plus 72. Is that right? That's not right. That's 120 plus, that is right, 72, which is 192. Okay? And how many students have SAT scores greater than 720? Approximately how many students? So go ahead and try to solve this one. Let me shift back up to here. So greater than 720, that's about 2%. So we need to find 2% of 1,200. So 1,200 times 0.02, which is 24 students. All right. That's pretty much how we use that normal distribution. Okay, questions 4 to 6 refer to the following information. So number of children is this top row, frequency is this bottom row. So how many people had 0 children? 1 time. How many people have 1 children? 2 of them did. So on and so forth. Table above shows the frequency distribution of the number of children in each of 8 families. Okay, so that's what I was trying to describe. Let m be the mean of the data set above. What is the value of m? So let me go back here. Bad format, sorry about that. But I'm going to try to solve for the mean. Okay, so it's sum over the total number of entries, right? So it is 0 times 1 plus 1 times 2 plus 2 times 4 plus 3 times 0 plus 4 times 1. Oliver, I believe it said 8 because 6, 7, 8, yeah. Divide by 8. That's the setup, okay? So let me write it over here. It'll be 0 times 1 plus 1 times 2 plus 2 times 4 plus 3 times 0 plus 4 times 1 all over 8. All right, so that is how much? That is 8, 9, 10, 14 over 8, okay, which is 1.75. Okay, 14 over 8 should be acceptable. If I remember that, you can fill out a fraction in the SAT, otherwise 1.75. Okay, let D be the standard deviation of the data set above. What is the value of D? So go ahead and try this one. Okay, so I might not be able to fit it all in here, but let me just say how to set it up. It is the entry minus the mean of 1.75 e squared. Okay, so it'll be 0 minus 1.75, that quantity, squared, plus 1 minus 1.75 squared. There's another 1, so plus another 1 minus 1.75 squared. Okay, and then there's 4 times, there's 2 children, so it'll be 2 minus 1.75 squared plus 2 times 1.75 squared, plus 2 times 1.75 squared plus 2, am I saying plus or minus? Okay, let me just write it out. Let me write out a few. So it'll be, let me write it over here. It'll be 0 minus 1.75 squared plus 1 minus 1.75 squared plus 1 minus 1.75 squared plus 2 minus 1.75 squared. This you would do 4 times. So plus that, plus that, plus that. And then 3 minus 1.75 squared happens 0 times, so don't need to do that actually. And then 4 minus 1.75 squared you need. Okay, so after you do all that, divide by 8, because there's 8 terms, right? So that would be your standard deviation. Let's just call it D squared. Sorry, that's the variance, which is 1.1875. Okay? The standard deviation is the square root of the variance, so it'll be 1.09 if you round it to the nearest hundredth. So don't do rounding, don't have a rounding error, so don't round here yet. Keep more decimal places. Round at the very end. Otherwise you might have some rounding error, which they could mark wrong. Okay. Okay, here are the good questions, in my opinion. Add 2 to each entry on the original list. Let MA and DA be the new mean and standard deviation set of the data set. Which the following is true? So how does the mean and the standard deviation change? So go ahead and try this. Okay, so in a time test like the SAT, you probably don't want to refine all the standard deviation and the mean again. Mean's not too bad, but standard deviation you can see is tedious, right? If you have a graphing calculator, actually, you can probably easily find the standard deviation because you could plug the values into the table and then you can find the standard deviation. So that's not too bad there either. But there's a much faster way to think about these problems. Okay, this is a time test. If you actually do it by hand, it will take you another few minutes maybe. So you don't want to do that. So I'm going to illustrate by drawing this distribution actually. Okay, so 0, 1, 2, 3, 4. Okay, so 0 happened once, 1 happened twice, 2 happened 4 times, 3 happened 0 times. So it looks like this. Pretend it's like a bar graph. I just drew lines, but pretend it's like a bar graph. So it's like a histogram kind of. Okay, so this is a distribution. Now it says add 2 to each entry on the original list. So do we add 2 to this or this one is the question, first of all. And we add it to the number of children. That's what it means. It's kind of vague there, but this is a frequency, so you don't add, it doesn't say add 2 to the frequency. So intuitively, it's probably the number of children. Okay, so number of children is this axis. Frequency is the y-axis. So if I add 2 everywhere, I'm just going to be shifting the whole thing up. So 0 plus 2, it'll be 2, 3, 4, 5, and 6. So it'll be the 1, 2, 4, 0, and 1 like this. Okay? So where is the mean now? The mean is somewhere up here. It's shifted up by 2 as well. You can just think, mean, you're summing up everything. So everything shifted up by 2, so the mean also shifts up by 2. Okay, so you can eliminate B and D right away. All right, now what about standard deviation? Isn't the spread exactly the same? Just the mean got shifted? So the standard deviation doesn't change. Answer is C. You can think about it like that, and you're done right away. You don't have to do any calculations. Of course, you can check by actually calculating if you have time, but again, that might cost you a minute or two, which you might need for some other problem. So I would not recommend that. Okay, now this is a little different. Multiply each entry by 2 on the original list. Okay, so how does the mean and standard deviation change in this case? So go ahead and think about it first on your own, and then come back here to see how I thought through it. So let's illustrate once more. Multiplying by 2. So 0 times 2 is still 0. 1 times 2 is 2. So there's an entry of 1 there. 2 times 2 is 4. So 4 is here. It would be up here then. All right. 3 times 2 is 6. So 6 has none still. And then 4 times 2 is 8. So that also has 1. Okay. So what happened to the mean here? The mean also shifted up by 2. It's going to be somewhere here. Okay, so the mean didn't really double, it shifted up in this case. Okay, so actually the mean did double, sorry. In this case, because you multiply by 2, shift up versus multiplying by 2 is almost the same. So for sure the mean didn't stay the same, so you can cross those two out. Okay, so you can see that, right? This is the mean somewhere here, probably between 1 and 2. Here the mean is between 2 and 4, probably like 3.8 or something like that. I don't know, I didn't calculate it, but of course you can calculate once again, but that's much slower. Not a little slower, that's much slower. Okay, now what about standard deviation? Does that change? Well, the mean is somewhere here. Now the spread is much farther. If the mean is here, now it goes all the way to 0 and to 8, versus here was around 2. It went from 0 to 4. The spread from the mean was much smaller here. Now the spread here is much bigger. So the standard deviation increased. So it cannot be the same. So the answer is A. Okay? So that's the way to think about these, in my opinion, that are much quicker than actually going to calculate the new standard deviation and the mean. All right, so hopefully this was helpful, and hopefully this illustration was helpful too, to see how the mean and standard deviation changed or didn't change. All right, as always, please like and subscribe if this video has helped you in any way.